monodromy part. So let me, first of all, just to make contact with the formulations that have been given in some of the other lectures, let me mention how the general setup is, as I've been using it, is related to what's been going on in the other lectures. So if the continuous part of G is u1 to the n minus d, then it's basically a representation of u1 to the n minus d in u1 to the n that we've been studying as we've been looking at these gauge linear sigma models. And underlying that is some lattice map that goes z n minus d to z to the n. And it has a co-kernel mapping to z to the d. And the image of the standard basis vectors from Zn, so I have EI, which has got a 1 in the ith position. The images of those are vectors Vi sitting in this lattice Zd, and those Vi are what span something like a reflexive polytope. So the actual gauge linear sigma model data that we've been using typically has the span of the VIs, or the convex hull of the VIs. In that particular case, turns out to be a Gorenstein cone. But the Gorenstein cone, I mean, the reason it's a Gorenstein cone is because we've kind of got this extra x0. And if you leave out the x0, if you omit x0, you end up exactly with this reflexive polytope description of the data that you need for toric varieties. And then the mirror construction, as I described it, of the matrix P capturing the polynomials that are occurring and the matrix T capturing the structure of the group being sort of mirror to, whatever that means, the transpose matrices factored in this other way, so that now transpose S determines the mirror group G hat, and transpose P determines the mirror polynomial W hat. That picture, in this special case of having a single x0 times a polynomial, turns into the more standard picture of taking the polar of a reflexive polytope to generate the mirror. So I just wanted to make contact with that, since it's shown up in some of the other lectures as the standard way that we describe mirror combinatorial data. Now, there's also something which happens with the parameters in mirror symmetry, and I've alluded to this, but I haven't spelled it out yet. So the parameters that we've been discussing mostly have been these parameters tau A, which were related to generators, or I should say perhaps a basis of the Lie algebra of our group, and their exponentials, QA is e to the 2 pi I tau A, actually turn out to be the most natural parameters to look at. On the other hand, when you pass to the mirror polynomial W hat will be some sum of monomials, and these monomials will have coefficients somehow. So this is the jth monomial, perhaps, in some funny notation. And those coefficients are what would naturally seem to form parameters in Cj hat. On the other hand, there's an action of u1 to the d on the variety that we're looking at. So if you look at this sequence that I had up here a moment ago, u1 to the n minus d mapping to u1 to the n, the quotient is going to be u1 to the d. That acts on the quotient space, and you can consider the invariance for the u1 to the d action. So you can form invariant quantities under the u1 to the d action. And if you do that, you learn, or if you do that, you get this sort of natural, at least toric version of parameters on the space of all polynomials. And that's what we want to identify with the QAs. So the specific identification is to identify RA with minus 1 over 2 pi times the sum of the QIA hat log CI hat. And that turns out, QIA, that turns out to precisely give it a possible identification. So of course, the Q for QA, I should exponentiate this, right? So there's also theta, which was just some real parameter. Theta A over 2 pi plus IRA is what we call tau A. And so if I form QA, which is e to the 2 pi I tau A, then maybe it's got this real part, which looks like CI hat raised to the QIA, a product of things of that sort. Well, that was norm times the phase, but in fact we should continue the identification, so the QA itself is just going to be the product of CI hat to the QIA hat. Sorry, it is hatted. So that's the identification that we use to try to match up the Q's, which were the natural coordinates that we saw coming from the part of the gauge linear sigma model that we're studying. In particular, the Q's are the things whose powers multiply the instanton contributions to correlation functions with parameters on the mirror story, the mirror model in some sense. Well, the most famous example, perhaps, of mirror symmetry is the quintic. So in the quintic case, I wrote out the matrix version of this the other day. In the quintic case, the mirror theory has some relatively simple-looking polynomial. So the polynomial data in the mirror theory was just C0 hat times, I'll repeat, well, maybe I'll put hats over the x's too. It doesn't matter so much, just for consistency. The mirror polynomial looked exactly like the original polynomial, the only difference being what group you had that was involved. And it turns out that there's a single invariant quantity for the group action in this case. And that invariant quantity, which I'll temporarily call Z, is the product of the C's, C1 through C5, divided by C0 to the fifth. So I imagine now, if I wanted to study the mirror theory, I would study the variation of Hodge structures associated to this family. I would recognize Z as the fundamental parameter which I need to look at in that variation of Hodge structures. And we can make a study of things such as periods, and of course the periods are multiple valued, so we can talk about the monodromy of periods as being one of the important aspects of this mirror theory. And it's that aspect which I want to relate somehow to things that are going on in the original theory. I'd like to understand what it is that has monodromy in the original theory and how I can interpret those monodromy transformations in the context of the original theory. So it's good to focus on the quintic example for a little while. I think we've seen by now the standard period that one writes down for the quintic. So there's a series, a nice infinite series. So this is really the mirror quintic. The standard series solution as a function of this parameter z, normalized exactly the way that I'm discussing it now, is 5n factorial divided by n factorial to the fifth times z to the n. I should have remarked when I had the coefficient there, and I still have the coefficient there, parameter there, that if you look in the Riemann surface spanned by z, z equals infinity. Well, z equals infinity corresponds to the to C0 vanishing. So z equals infinity is the Fermat quintic. Z equals 0 is another special point. Z equals 0 corresponds to one of the C's vanishing and C0 not vanishing, and that corresponds to what's often called the large complex structure limit point. That's the point about which we've just made a series expansion. since the series was a power series in Z. And there's one additional point, which is singular, which in the normalization I'm using right now is minus 5 to the minus 5. That's the same minus 5 to the minus 5 that we calculated from the perspective of the other theory this morning. That's the location of the singular point, just thought of as a when this polynomial, as it depends on the C's, acquires an additional singularity. That's the one additional place where that can happen. So there are these three special points where something interesting happens. And right now we're looking near Z equals 0, the large complex structure limit point. I just wrote down the series solution for you. But in fact, so that series solution satisfies in a natural way a differential equation, looks like d phi equals 0. And you can write that differential operator very explicitly if you like. It's z d by dz to the fourth minus 5z times 5z d by dz plus 1, 5z d by dz plus 2, down to 5z d by dz plus 4. That's the minimum order differential operator that annihilates the series that I mentioned. And it admits other solutions, but those other solutions are multi-valued near z equals 0. So to understand how the multi-valuedness works, it's easy to write a sort of formal power series solution in the following form. So I could write sum n equals 0 to infinity, 5 alpha plus 1, 5 alpha plus 2, 5 alpha plus 3, well, whatever. I'm going up to 5 alpha plus 5n, and then I'm dividing by alpha plus 1, alpha plus 2, on up to alpha plus n, all raised to the fifth power, z to the alpha plus n. So that's a slight generalization of the series solution that I gave a moment ago, which had alpha equals 0. When we apply the differential operator in this case, so the differential operator applied to this function phi alpha of z, it turns out to be alpha to the fourth, z to the alpha. So if we can interpret this quantity alpha as having a fourth power as being 0, then we can get solutions. And in fact, the natural way to write down all these solutions now is to work in the ring C adjoin alpha, mod alpha to the fourth, and to treat this as a formal parameter whose fourth power is taken to be 0. Do the expansions in that formal parameter whose fourth power is taken to be 0, and you'll locate the solutions. So we get a four-dimensional space of multi-valued solutions. To sort of understand the multi-valuedness, you notice that what happens when you take log z to log z plus 2 pi I, phi alpha of z gets multiplied by e to the 2 pi I alpha times phi alpha of z, because of this z to the alpha factor in the series expansion. So I find a four-dimensional space of solutions depending on this formal parameter alpha with the property that the matrix which describes the monodromy is just given by multiplication by e to the 2 pi I alpha in this ring C of alpha mod alpha to the fourth. Organizing the solutions that way is maybe not immediately apparent when you first write them down, but it's a very convenient way, and as we'll see, sort of relevant to the whole discussion of describing what the behavior of all the solutions is. So that describes locally what the periods all look like near z equals 0, and we can also give a description locally of what the periods look like near z equals infinity by writing a similar formal power series solution which is valid near z equals infinity. And the difference is that I'm going to write now a series in negative powers of z. So I'll call it sum m equals 0 to infinity, alpha plus 1 up to alpha plus m minus 1. And I'll raise that to the fifth power, divided by something close to what I had before, 5 alpha plus 1 up to 5 alpha plus 5m minus 1. And then that's z to the minus alpha minus m. So you're led to a series in negative powers of z because you want to expand. This is an expansion. It's really a series in z inverse, if you like. It's an expansion near z equals infinity. We've got the same differential operator. which we calculate in this case, turns out to be minus 5 times minus 5 alpha plus 1, minus 5 alpha plus 2, minus 5 alpha plus 3, minus 5 alpha plus 4, times z to the minus alpha plus 1. So if this quantity is 0, we get solutions. And we see that we get solutions, in fact, 4 independent solutions in this way, corresponding to values of alpha being 1/5, 2/5, 3/5, 4/5. When we look again at the behavior under log z goes to log z plus 2 pi I, we again get multiplication by e to the 2 pi I alpha, but this multiplication by e to the 2 pi I alpha is now multiplication by a 5th root of unity. So this time, instead of having that funny ring structure and a matrix in that ring describing the monodromy behavior of the periods, here we just get multiplication by 5th roots of unity. There's an action on the moduli space of Z5 near that point, and splitting the periods into eigenfunctions is essentially how we got these multiple value versions of the periods in that particular case. So if I could just reiterate my picture of the Riemann surface, here at z equals infinity, we got this order 5 monodromy. Here at z equals 0, we got the e to the 2 pi I alpha on c alpha mod alpha to the 4th. And there's one additional singular point. There's no good formal power series solution. But it is true that the monodromy around this point, in a simple case like this, can actually be derived from the monodromy around here and around here, just by utilizing the fact that on the sphere, a loop around this point is just a composite of a loop around this and a loop around that. Well, you have to worry about how you analytically continue, exactly where you do the analytic continuation, sort of to run down from the North Pole to the South Pole. But so long as you do that carefully, you can run around each of these two loops and thereby describe what happens with monodromy around the third point. Yes?
Why do you say there's no good series solution around C equals?
Sorry, let me rephrase that. This kind of writing of a formal power series solution by solving some little recursion relation that you get from the GKZ setup doesn't work at that point. Of course, there's a series solution.
There's a series solution. It has, as you say, I mean, it has something like a 4-term recurrence relation. It's not fun to solve.
It's not fun to solve, right? It's right. These 2 points, because they're kind of related easily to sort of toric boundary points in the moduli space, you can write down the recurrence relation pretty simply. Okay, so I'd like to interpret this on the mirror side, on the original side, I should say. I'm on the mirror side right now. I'd like to interpret this on the original side. And on the original side, of course, I had my parameter q. So q equals 0 is where we've done instanton expansions. We found exactly the same location, q equals minus 5 to the minus 5, and then q equal infinity is a point that we haven't really considered yet. It's certainly far away from being able to be analyzed directly in terms of these instanton expansions. And near q equals 0, yes, so what structure is it that we're now going to try to understand in terms of monodromy? Well, back in this Z picture, the periods that we're looking at essentially span the third cohomology of the hypersurfaces x hat as they depend on parameters in some form or another. So we're the parameter is z. And as you move around in the moduli space, the basis that you've chosen for that third cohomology changes. So the third cohomology bundle cannot be trivialized over the entire sphere. It exhibits the monodromy, and that monodromy behavior is exactly what we're picking up by noticing the multiple valuedness of the period integrals. There are lots of aspects to mirror symmetry. Mirror symmetry, among other things, tells you that the third cohomology of xz hat should have been related to the the even cohomology of the original x, and we could say as it depends on the parameter q, although the parameter q is not so transparent here, the meaning of the parameter q. And in fact, there's a natural bundle structure. So there's a natural bundle whose fiber is the even cohomology of x, but which has some non-trivial monodromy behavior, and it's that monodromy behavior which we're trying to get our hands on. Near q equals 0, we can actually describe this structure in the following way. So near q equals 0, we started out with we could start out imagining taking intersections of triples of divisors on this Calabi-Yau threefold. And if you know the Poincare pairing on the even cohomology, calculating the triples of divisors, so knowing these numbers, is equivalent to knowing the multiplication structure on cohomology if you're given the Poincare duality pairing. So what we'll assume, and again, thinking about the structure of the conformal field theory, this is a reasonable assumption to make. What we'll assume is that the Poincare duality pairing isn't changing somehow as we vary things, but that this set of triple intersection numbers is somehow q-dependent. In fact, we've already seen that the physics naturally calculates these correlation functions, which in the q equals 0 limit are just the classical intersection number, but have a q-dependence away from the q equals 0 limit. So that's, in a way, the intrinsic description of what it was we were calculating with the physical correlation functions. And so the reason you can then think of this as essentially being the product of D1 and D2 paired with the third divisor D3, those are complementary dimension, and that's the basic explanation for why there's an equivalence between calculating these triple intersection numbers and working out the multiplication structure on this thing as an algebra. So the interpretation is that d1.d2.d3 plus the quantum corrections, so it's going to be a sum, say, n positive, some coefficient times q to the n, that this is a deformation of the ring structure, and it's the thing which we're capturing and which has the potential of having some monodromy in this situation. So how is this related to the computation we did a moment ago? Well, for the quintic, in the case of the quintic, this so-called quantum cohomology ring structure, in which we've replaced the intersection product with a modified version of the intersection product, the quantum cohomology ring, the usual cohomology ring, the classical cohomology ring, has this structure of q adjoint alpha mod alpha to the fourth, right? The fourth power of the generator is trivial, just on dimensional grounds, and so the structure that we saw a few minutes ago was a kind of monodromy structure, which was the action of e to the 2 pi I alpha on this classical cohomology ring. And that structure can be described intrinsically in the following way. Excuse me 1 second while I get to the right page. So I can think of that structure as, as being represented by some matrix which just looks like 1, 1, a half, a sixth, and then 1, 1, a half, and then 1, 1, and 1, right? This is the basic kind of monodromy that we're expecting to have. And let me call that transformation T. It's describing the behavior, hello. It's coming?
again the beginning.
Turn on.
That's okay.
Just let it out, Cam. Here we go. So our first clue about what kind of structure we want to put on the bundle is given by that monodromy transformation that we saw, which just looks like e to the 2 pi I alpha on q alpha mod alpha to the fourth. And in fact, this relation in quantum cohomology is, well, I guess what I'm really trying to do is use the classical cohomology to describe this action, but you can also rewrite it in terms of the quantum cohomology if that's something that you'd like to do. So there's a slight extension of the physical situation that we've studied up until now. So up until now, we've actually been studying the two-dimensional quantum field theory that was associated to the attempt to compactify string theory. But if you actually compactify string theory and don't just look at the two-dimensional quantum field theory, string theory has additional features. Including some things which have only been, were only recognized sort of late in the game, some things called D-branes. And D-branes it's been proposed that D-branes can be identified in the context of this topological A model that we're now discussing with the derived category of coherent sheaves, bounded derived category of coherent sheaves on X. Okay, so that seems like a pretty severe mathematical machine to drag into the picture at the moment. However, there is, once you've realized that the natural structure that you probably need to be studying isn't just captured by the topology, but actually has additional structure, including the derived category, you can ask about possible automorphisms of the derived category. And the first automorphism of the derived category that you might look at is the one that was represented a moment ago by this matrix T. So this is just some kind of change of basis within the derived category that I'm not going to attempt to assign a geometric explanation to. But Kontsevich in 1996 proposed a class of automorphisms of the derived category, and I'll start out by telling you the simplest item in that class, which seem to be closely related to this quest for understanding the monodromy on periods back in terms of this Gates linear sigma model or related theories, including the D-branes that we're now discussing. So here's what Kontsevich proposed to do. He proposed to consider the diagonal inside of X cross X and to look at the ideal sheaf of the diagonal. So there's a natural automorphism of the derived category which takes an object to the push forward by the second projection of the pull back by the first projection of the object tensored with this ideal sheaf. And it turns out that to make sure that this is an invertible transformation on the derived category, the Calabi-Yau condition is exactly what you need. What's required for this to be an automorphism. So it's a very natural sort of thing to think of doing once you've decided to look for automorphisms of the derived category. And if you understand there's this refinement of cohomology to the derived category coming from string theory, then you might think that derived category automorphisms are the way to go. So what's the effect of this on cohomology? Well, the effect on cohomology takes gamma to gamma minus an integral of gamma wedged with the Todd class of the tangent bundle multiplied by the identity map on X, where the 1 on X generates H0 of X. So that's a simple calculation of the effect of this automorphism on cohomology, and it leads to a calculation. So you can calculate for the quintic. So now we really are dealing with the quintic, not the quintic mirror. You can calculate the Todd class for the quintic and figure out a matrix for this automorphism. It's 1, minus 25, 6, 1, 0, 0, 1, minus 5, 0, 0, 1. So this, So that's the components of the Todd class. This is the total Todd class in some sense. So this is how that particular automorphism of the derived category behaves. Well, so what did Kontsevich do? He said, let's calculate T times S. Don't ask me why he thought of doing this. So you calculate T times S, and here is the very explicit answer. 20 thirds, 1, 1, 1 half, minus 5, 0, 1, 1, and minus 5, 0, 0, 1. So there's T times S. And then you calculate, then you observe that T times S raised to the 5th power is equal to the identity. So here I started with this matrix that I know captures the behavior of whatever monodromy problem I'm trying to formulate near Q equals 0. Here I've found a natural automorphism, and if I compose these two things, I end up with something that has order 5. So what's the interpretation that's supposed to be of this calculation? The proposed interpretation in terms of our moduli space here, where we had Q equals 0, Q equal infinity, and Q equal minus 5 to the minus 5, is that the Kontsevich transformation somehow represents the monodromy on the derived category that you get by going around that point, the one where I said it was a little tricky to calculate directly with series solutions on the quintic side. This corresponds to the e to the 2 pi I alpha transformation. And the evidence for it, at the moment, just one example, but I'll just discuss the status of this problem in a few minutes. The evidence for it is that here we got the order 5 automorphism that we were expecting. And indeed, the relations on the fundamental group here say that the product of these 3 loops, if you choose the order correctly, should be the identity. So it's really remarkable that making this very geometric computation, the Todd class, and then just multiplying by that particular automorphism, you end up with this finite order automorphism. And Kontsevich at that time, in '96, verified this proposal in the sense that I've just mentioned, that you get, after composing with the e to the 2 pi I alpha, you get a finite order transformation of the expected order for all known one-parameter examples with a so-called Fermat point. And that Fermat point tells you something about the finite order monodromy that you're expecting to see. So there's been a lot of study of this in the intervening years, and the current best description of the situation is that there is a bundle over this moduli space which represents the bundle of D branes in the physical theory. And what we expect is there should be geometric transformations a la Kontsevich in some way or another, corresponding to monodromy around various loops. So what other kinds of geometric transformations could we have? Well, in fact, Kontsevich already proposed a generalization of the simplest case, which he was working with. So Kontsevich's suggestion was to start with some other sheaf F and define I sub F to be the kernel of the natural map from the exterior power of F and its dual into the structure sheaf of the diagonal. So this is still, so IF is on X cross X as before. And then we can make the same kind of transformation with respect to F and ask the question, when is it that this transformation will behave as, will induce an automorphism, will be invertible on the derived category? Well, the condition is kind of cute. You consider what the values of xk of F with itself are, and the condition that you need to make sure you get an automorphism is that xk of F with itself is one-dimensional if k is equal to 0 or n. N is equal to 3 here, and 0 otherwise. In fact, Kontsevich made this proposal in arbitrary dimension, and the only reason I'm sticking to 3 at the moment is that I've stuck with 3 all through the lecture, but in general we would possibly consider 0 and n. So it's something like a homology sphere for X, right? It's got the if you think of X as some kind of homology or cohomology theory, it's got the expected behavior for a homology sphere. And the case above was the case where F was the structure sheaf of X, and the fact that X k O, that's just HK of O. The fact that that is non-zero exactly at 0 in the top is one of the characterizations of Calabi-Yau manifolds. It's calculating those particular Hodge numbers. So there have been various attempts to find sheaves like this, and there have been some modifications of this original proposal. But so far, through work of Seidel and Thomas and of Horja, many examples have been checked. So what that means is that looking around in some explicit moduli space, you can find in that explicit moduli space appropriate geometric transformations, either based directly on these homology sphere for X type of sheaves, or in some cases on generalizations of this which are defined on submanifolds of X rather than being defined on all of X cross X itself. You can find very natural looking automorphisms of the derived category which reproduce all of the monodromy behavior that you might have expected.
Excuse me.
Yes?
So what kind of F's come out other than OX?
So, for example, if you have a rational curve on the Calabi-Yau manifold, the structure sheaf of that rational curve also has this property. So that's another example of an F which can come up. It's actually not known how to classify the F's which come up.
So any rational curve on the Calabi-Yau manifold?
Yes, I believe so.
No matter how it's sitting inside the manifold somehow?
Well, let me be safe and say the normal bundle should be O minus 1 plus O minus 1, but that's not actually terribly restrictive.
I see. And also, when you say the bundle over moduli should represent D branes, do you have a precise sense?
Well, so to Depends on whether I can define D-branes or not.
How about if you look at the other side? You said that there's a correspondence between D-branes and the derived category of coherent caves. There's some correspondence of that sort on a previous page.
So physicists believe in D-branes,
Right.
but physicists don't quite know what D-branes are.
Right.
So the proposal that's sort of currently the favorite of at least many of my friends is that in this A model theory, the correct description of D-branes is in terms of the derived category.
Right, and we know what they are. We know what the derived category of coherent
B
caves
model,
are.
thank you.
So you seem to be saying there should be a bundle over the moduli space whose fibers are, in some sense, the derived category of each fiber. Is that what you're saying? Of each Calabi-Yau in that family, something like that.
Jacques points out that I said it slightly wrong, that was the D-branes on the B model. The D-branes that I wanted on the A model, well, I always get slightly confused about which parameters I'm looking at here.
The D-branes of the B model are supposed to be objects in the derived category.
Right.
In the A model, you can say something about Fukaya.
The Fukaya category, yes, right.
So in either case, anyways, so what you're saying is there should be something like a bundle over the moduli space.
So the most primitive description would be that there are two bundles over the moduli space, which on the mirror side, you have the bundle of H3s, which has a well-defined monodromy, can be calculated with periods, and we know what it is as a bundle. It's fiber by fiber, it's H3.
Right.
On this side, fiber by fiber, it should be the cohomology of the even cohomology of the space, or possibly some refinement of that, such as the derived category. What's tricky is that we only know near Q equals 0 how to define that bundle. So the interpretation of the physical theory as being related to the nonlinear sigma model on the Calabi-Yau manifold, that only works near Q equals 0. When you go out to further regions like Q equals -5 to the -5, you don't have an interpretation like that directly. So there's this. So Kontsevic's notion is that somehow whatever is going on, there will be you'll be able to express everything throughout this moduli space somehow in terms of the derived category of coherent sheaves on the space, and that it's automorphisms of the derived category that we should be looking for as the natural analog of the monodromy transformations from the other side.
Right, but the sense of bundle, when you say bundle, therefore, it should be something like a stack. Is that what you're thinking? Sheaf of category.
There is a precise thing that he could say in the context of his lectures, which is in the context of these gauge linear sigma models that he was talking about. We could talk about the space of possible boundary conditions if I wanted to
Right.
formulate these things on Riemann or on
Right.
two-dimensional manifolds with boundary, and then ask how those boundary conditions vary with these parameters, and perhaps pick up monodromies there. No one's really come up with a satisfactory account of it in that language, but that's the language you'd like to phrase it.
Let me try to explain it another way. This parameter Q is essentially measuring the Kähler class of the Calabi-Yau manifold. And we don't know how to interpret it geometrically so well once we get outside of a small neighborhood of Q equals 0. It's an exponentiated Kähler class. If you start talking about making stacks and treating the moduli problems as standard moduli problems in algebraic geometry, what that really means that you have in mind is letting the complex structure vary and consider how this depends on the change of complex structure. It's not depending on the change of complex structure, it's depending on the change of Kähler structure. And so it's a little difficult to formulate in the traditional language that mathematicians would use. Okay, well I wanted to try to draw a picture for you of what the moduli space looks like in example 2. So I drew one funny kind of picture earlier, and I'm going to try to draw a slightly better picture. This is a picture that I'm very fond of, but it's hard to get it right, I have to say. And the reason that it's hard to get it right, where did it go? I need to copy it. Oh, there we go. The reason that it's hard to get it right, I can't explain why it's hard to get it right. I've calculated it a number of times, and it's not sort of in the usual coordinates. So what I want to do is imagine writing the Q1 and Q2 axes backwards from what one usually does. And the reason that I end up wanting to write the Q1 and Q2 axes backwards pardon me while I try to find my picture to copy. Oops. Is that I can then sort of relate the cone description of this parameter space to the Q1s and Q2s. So this was my sort of picture with R1 and R2. But remember, the relation between the Q's and the R's is that Qj, or the real part of Qj anyway, is e to the minus 2 pi Rj. So when when R1 gets large, Q1 is going to get small, and I'm imagining this point as being sort of out at the infinite limit of R1 and R2, but I'm denoting it here as the Q1, Q2 point, and then the axes sort of go like that. So I also had this point, Q2, this line rather, Q2 equal a quarter. Something interesting was happening there. I have other sort of axes. So what are these other axes about? These other axes have to do with the natural coordinates that I would get if I used, instead of, so R1 and R2, this cone gives me some natural set of coordinates which are valid for large values of R1 and R2, and lead to exponentiated coordinates Q1 and Q2. And I can do that for each of the other cones in this cone picture. So I've divided the R into regions according to the R1, R2 space into regions according to the behavior of the moment map. And now I'm imagining exponentiating the coordinates to get some kinds of coordinates that ought to be valid near infinity in each of these four directions. So, for example, over here, it looks like Q1, Q2 to the 1/2, and Q2 to the 1/2, to the minus 1/2. That turns out to be the expression for these infinite coordinates near infinity in terms of these coordinates near infinity. And indeed, as you might have expected, when you move along this Q2 axis, you'd like the Q2 coordinate to go to the other side, right? Here it's small, and over here it's large, so it's represented by Q2 to the minus 1/2. Then there's the one that I always seem to mess up when I try to draw this thing, and that's the additional component, the one we were calling delta this morning. So it's supposed to go through that intersection point. It's supposed to be tangent here, and then it kind of comes down and misses all other points. No, it doesn't meet anything in particular. So this is delta. This is a real picture of the moduli space associated with example number 2. And the transformations along here and along here are given by some appropriate e to the 2 pi I alpha 1 and e to the 2 pi I alpha 2. That's the basic story of making an analysis of what happens when you shift, you want to shift the angle of theta, the angle of q, which is called theta, by 2 pi times an integer. And when you make that shift by 2 pi times an integer, that's essentially multiplying by this e to the 2 pi I alpha. On the other hand, we learned through computing many examples in the early 90s that it's exactly this kind of transformation taken with respect to generators of H2 acting on the total even cohomology, which characterizes the points that are supposed to be mirrored to the large complex structure limit points. So you could find places to do the instanton calculations in nonlinear sigma models by identifying points that had this kind of monodromy behavior. So this is sort of the easy part, is identifying the monodromies around these curves as measured being near the point Q1, Q2. It's not that hard to work out what this monodromy is from this point of view. And Horja found a sheaf, which I should have looked up, but I don't recall exactly. But he found a sheaf of Kontsevich type for this example, which actually realizes this monodromy. What's much more challenging is to figure out what the monodromy behavior is along a curve like this, or even along a curve like this, because there's a non-trivial conjugation which happens when you compare the loop here to the loop here. And again, in this particular example, Horja was able to find an explicit construction. It's not quite the Kontsevich sheaf F. It's something that's supported on a smaller subvariety. Sorry, I take that back. Around this point, he was able to verify that Kontsevich's using the structure sheaf as Kontsevich proposed is exactly what it is that you need to do. But the fundamental group of the complement of the discriminant locus here is a fairly complicated thing. And to figure out a systematic way of addressing what all the possible loops are and what the geometric interpretations of them might be is something that's still very much under development. I mean, this is, to me, a really interesting development from the last 3 or 4 years of trying to figure out in much more detail what the interpretation of the behavior of periods is, not just at this point or close cousins to it, where we've had the traditional curve counting idea, but at other points as well.
So how does one find such monodromy away from the large radius limit?
So first you calculate it on the mirror side. So to find out what the monodromy is, you calculate on the mirror side. And then you try to figure out, can you find some geometry which would reproduce this same monodromy? There isn't yet, aside from the sort of general conjecture that maybe the original one Kontsevich wrote down with O is the one that's associated to the big component in the discriminant locus. Aside from that conjecture, there aren't real specific conjectures about what the geometric interpretation should be. You know, I was kind of hoping that a few examples would show what the natural conjecture was, but the answer is, at the moment, we need a few more examples before we can figure out what the natural conjecture is. Anyway, that's probably a good place to stop for today.